only one of infinitely many correct answers. So you need to find more. And the first that you can find is by thinking about, well, what's another angle that has the same cosine as that angle? Negative inverse cosine does. Right, cosine is even, so if you stick a negative sign in front of the number in question, you'll get the same cosine. Once you find those two solutions, you can add 2 pi k's. There are some subtleties here. If I ask you to solve cosine of x is equal to 25, you shouldn't do this at all, right? How many angles are there which result in a cosine of 25? None. There are no solutions to cosine of x is equal to 25. You can do the same thing with sine. The 2 solutions that you'll find will be inverse sine and pi minus inverse sine. Take those 2 and add 2 pi k's, because sine is 2 pi periodic. If you want to solve tangent is equal to a number, one solution is inverse tangent of that number. To find all the solutions, just add pi k's. So, with that in mind, let's think about solving complicated trig equations. And maybe a good warm-up is, let's solve this number 2 first. Let's find all solutions to the equation 5 times the tangent of x plus 2 is equal to 1. Does that equation right now look like trig function is equal to a number? Well, it almost does. Right? You need to do this much algebra. What do you get when you, so let's take that and solve it for tangent, because I see a tangent in there. And maybe it's not so big a step this time so that it won't, well, let's set t equal to the tangent of x, so this equation becomes 5t plus 2 is equal to 1. Does that look like an equation that we can solve for t? It does, right? Subtract 1 from both sides, subtract 2 from both sides, and then divide by 5. So I guess you'll get t to be negative 1 over 5. And so, what do we get? We get tangent of x is equal to negative 1 over 5. Is that now a simple trig equation? Something that looks like a single trig function is equal to a number? So we can appeal to one of these 3 sets of instructions. I guess it's tangent, so we should use this one. So the solution that I wind up seeing, well, first let's check one thing. How many people have their unit circle on top in front of them right now? So by looking at your unit circle, do you see any angle on that unit circle that has tangent equal to negative 1 over 5? No. OK, so that means we just need to use inverse trigonometry. So the solutions that we'll get are x equal to tangent inverse of 1 over 5, negative 1 over 5. There, that's the elementary solution, if you like. And then you can take that and you can add pi. Okay, that gives you all the solutions. People feel pretty okay? Maybe I'll point out one thing. We graphed inverse tangent when we developed inverse tangent. Is inverse tangent even or is it odd? Odd, I think. So what can I do with that negative sign in front of that inside of those parentheses? You can pull it out fine. And that's not a huge simplification, but it's a simplification. That's the same thing as negative tangent inverse of 1/5 plus pi k. Everyone feel pretty okay? So the first bunch of things I want to do today are think about solving trig equations of increasing complexity. And maybe the first one I'll suggest is let's try to solve this equation. 3 times the tangent of 2x plus 1, 2x minus 1 rather, plus 2 is equal to 1. Yeah.
So you said that the inverse tangent is going to be equal to the negative inverse?
Did I lose the negative sign? Yeah, so tangent, inverse tangent is odd. So that means tangent inverse of negative anything is equal to negative tangent inverse
Oh,
of
it's
that angle.
negative, okay.
Yeah, so,
I didn't see that it was negative.
yeah. Nice. So let's try to solve an equation that looks like that. So step one, let's just try to solve it for tangent of that stuff. So what'll I do? I'll say, well, let's just replace tangent of 2x minus 1 by 3. So the equation will become 3t plus 2 is equal to 1. So what do you get when you solve that for t? Negative with 1, I think. You'll get t equal to negative 1 over 3. And it's a linear equation, right? So the reason I didn't want to do it is because it's pretty straightforward. So this equation will become tangent of 2x minus 1 is equal to negative 1 over 3. So here's what I'll do next. This thing inside of the parentheses makes it look complicated. So let's just set that thing inside of the parentheses to be a new variable, call it u. So I'll set u equal to 2x minus 1. So this equation will become tangent of u is equal to negative 1 over 3. Is this equation something that you can now solve for u? What are the solutions to that equation? So I'll get u equal to tangent inverse of negative 1/3 is one solution to that equation. What other solutions are there? And maybe I'll even take advantage of the oddness again. I can pull that negative sign out. So I'll get 2x minus 1. So that was like the thing that we called u. Is the same thing as negative arctan of 1 over 3 plus pi k. Oh, but look at that. Now it's 2x minus 1 is equal to some stuff. Does that look like something that's easy to solve for x? Yeah. X's only appear on the left-hand side, and the left-hand side's all linear. So what do you need to do to that to solve for x? Add 1 and divide by 2. So let's just do that. We'll wind up with x equal to, maybe color coding will help, negative tangent inverse of 1/3 plus pi k. It doesn't matter where you put the plus 1, but maybe it seems most natural to have it right there. Divided by 2. Everyone feel pretty okay about that? Cool. So let's keep on going. So let's try this next one. Let's solve the equation 4 cosine of x plus 5 is equal to 4 times the square of the sine of x. And let's think about what we did on the previous bunch of examples. We went and declared the trig function that we see to be a variable. We called it t in the case of tangent, s in the case of sine, c in the case of cosine. Not for any deep reason, just because that's the letter those functions' names start with. If I do that here, though, I'll be in a weird situation. I would want to rewrite that as 4c plus 5 is equal to 4s squared. That looks like an equation with two unknowns. One equation with two unknowns, generally speaking, you can't solve it all the way. So I want to do something to get this either just in terms of sine or just in terms of cosine. Is there a relationship between sine and cosine you can take advantage of? What relationship are you thinking about?
Square versus
Sine equals 1.
Yeah, Sine squared plus cosine squared is always equal to 1. So sine squared of x plus cosine squared of x is always equal to 1. Do you think you could take that and solve it for sine squared? Yeah. You'll get sine squared of x is exactly the same thing as 1 minus cosine squared of x. So that means I can take this sine squared of x and replace it with 1 minus cosine squared of x. Let's see what we get. So let's make that substitution. We'll get 4 cosine x plus 5 is equal to 4 times, parentheses, 1 minus cosine squared of x. How many people would be think they would be likely when they did that step to forget to put the parentheses around that whole big thing? Okay. Do you see why they were important though? Yeah, so you need all of sine squared to be multiplied by. Nice. So now this is now an equation with just one trig function inside. Let's simplify it a little bit, I guess. Yeah, let's just set cosine x equal to c and see what this becomes. I'll get 4c plus 5 equal to 4 times 1 minus c squared. So that's now a polynomial equation. It's of degree 2. So it's something that can be solved by, I don't know, the quadratic formula. Maybe you can do some fancy factoring, but the quadratic formula is something which will always work. And at this point, I'm kind of just stalling, because I think that you guys can solve that and just tell me what C is. How many people want me to talk through the algebra and solve that for C? Okay, then I will do. So I guess I should distribute that 4. That's a thing that would make things simpler. So I'll get 4c plus 5 is equal to 4 minus 4c squared. If I want to use the quadratic formula, I should put everything onto the same side and have 0 on the other side. Since the c squared on that side is negative, I'll move everything to the right so that the c squared will have a positive number next to it. Not for any big reason, I would just rather have the leading coefficient be positive. I'll get 4c squared, add that to the other side, plus 4c, plus 5, I'll subtract 4 to the other side, so that'll leave me with plus 1 is equal to 0. Fair enough. Now, well, let's see, I could apply the quadratic formula at this point. You could, I happen to, well, by the magic of the fact that I've already done this example about an hour ago, I know what the answer is, so I know how it factors. How does this factor? Sometimes factoring isn't so straightforward with non-monic polynomials, so let's just use the quadratic formula. We'll see that it should factor nicely. Gesundheit. So by the quadratic formula, you'll get that the independent variable is negative 4 plus or minus the square root of 4 squared minus 4 times 1 all over 2 times 4. So that's just writing down the quadratic formula. Now let's simplify. The thing inside of the square root, what's the thing inside the square root? 0. Square root of 0 is 0, so that's nice. So I'll just wind up with negative 4 over 2 times 4. So what is that? Negative 1/2. Nice. So we wind up with only one value that c could be. C is equal to negative 1/2. Now we need to solve the equation cosine of x is equal to negative 1/2. And so how do you do that? Well, you find a preferred solution to cosine is equal to negative 1/2. There is, in general, the inverse trigonometric way of seeing it. Then you find another one by sticking a negative sign up front. But before you do that, you should look at a unit circle. by looking at the unit circle, do you see some angles where cosine is negative 1/2? So that gives me two starting solutions. From those two starting solutions, how can you write down all of the solutions? Yeah, x equals pi over 3. I call it a plus or minus all, right? Plus or minus? The k, whatever you write down this k, the k is supposed to be an integer. Integers are allowed to be negative already, so you don't need the plus or minus, but I guess it doesn't hurt anything to remember that it can be a plus or a minus. How many people doing it on their own instead had like a negative pi over 3 right there? Yeah?
Isn't it supposed to be cosine is equal to negative 1/2, so 1 to be in quadrants, 2 and 3 in that quadrants, 1 and 4?
Aha. Oh yeah, negative 1/2, right? Cosine of pi over 3 is positive 1/2. So I didn't exert any critical thinking. I just like trusted the sounds that I heard.
So 1 to be 2 pi over 3 and 4 pi over 3?
I think there should be a 2 pi over 3 there. Did you actually say 2 pi over 3? Okay. Okay, well then I just listened poorly. That's on me. Cool. People feel pretty okay about solving trig equations like that? So the whole idea is figure out what a trig function has to be equal to. Get down to a simple trig equation. Then the simple trig equations, those have solutions that you can either find by looking at a unit circle and seeing if you just see some solutions, or by appealing to an inverse trig function. Let's do one last one before we start doing some new stuff. Let's try to solve this trig equation. Tangent squared plus secant squared is equal to 1. And so again, we see that there's like more than one trig function in play. There's a tangent and there's a secant. So like, you could write it down like that, but then it looks like there are multiple unknowns in play, which makes it hard to solve. So we don't want to do that. Oh, you couldn't even see what I wrote. That's okay. There's more than one unknown, so it looks like it's hard to solve. Instead, we'll try to find some relationship between the trig functions we see. So let's see, those who read the book really thoroughly and remember all the details in the book in addition to notes will recall a fact about trig functions which I haven't stated in class yet, namely the other Pythagorean identities. Who remembers, who can think of what those say about tangent and secant? What do they say?
This tangent squared of x is equal to sine squared of x over cosine squared of x.
Yes, that's not one of the Pythagorean identities, but let's chase that. I will formally state the other Pythagorean identities, maybe by the end of today, maybe at the start of next time. But that's a good idea too. Since we don't know the other Pythagorean identities, let's use something we do know. I know that tangent is sine over cosine. So let's rewrite this as tangent squared is sine squared x over cosine squared x plus, let's do the same thing for secant. What is secant squared? 1 over cosine squared. Good. 1 over cosine squared x is equal to 1. So that's better because I'm more comfortable with sines and cosines than am I with tangents and secants. But if I go and try to like just re-express things as a simple equation, there are still like two unknowns, so I'm still like posed. But do we know a relationship between sine squared and cosine squared we can take advantage of? The sum of their squares is equal to 1. Before we do that, maybe I'll do a bit of simplification. I see a fraction plus a fraction, and those fractions have the same denominator. We may as well write it as a simple fraction. Sine squared x plus 1 over cosine squared x is equal to 1. Nice. So now we'll use the Pythagorean identity. So apparently I can, yeah, it's a question?
Could you just do like tangent squared plus 1 equals secant squared?
Yeah, so if you happen to remember the other trig identities, you could say, well, I know that tangent squared of x plus 1 is the exact same as secant squared of x. If you want to use that, you could just, I guess, rewrite that secant squared as, so I've got tangent squared of x plus tangent squared of x plus 1 equal to 1. Does that look like you could solve it for tangent? Yeah, so at the risk of committing the fault of like changing horses midstream, we could follow that procedure. Maybe what I'll say is let's put this, so it will be shorter, but it required you to remember something which I hadn't actually taught. That's why I didn't want to follow this strategy. So let's finish it this way and see if it agrees with the solution that you get out of that. So
So you want me to do it that way?
if you want to, I think that I'll talk through it both ways. Yeah, so go through it that way. See if you get the same answers as I will get in more time. So I see sine squared plus 1 over cosine squared of x. I can either rewrite the sines as cosines or the cosines as sines. Would people rather I get the sines so I'll either wind up with an equation involving sines or an equation involving cosines. How many people would rather end up with an equation involving sines? Equation involving cosines. Okay, I think the cosines have it, so let's rewrite. Let's use the fact that sine squared is equal to 1 minus cosine squared. So I can rewrite the numerator as 1 minus cosine squared x plus 1 over cosine squared x equals 1. Everyone happy enough? Does that look like an equation we could solve for cosine? I think so. So I guess we didn't follow that. We instead do express it in terms of cosine of x. I mean, I don't know. Do people? So presumably a lot of people are already doing the algebra. People don't want me to talk through the algebra of getting cosine on its own. Okay, then I will go through the algebra. So
Sine, like you're expressing it as sine, it would just be the other way around.
yeah, so instead this cosine squared would become 1 minus sine squared.
Okay.
So the other way, something would be the other way around, but I guess more specifically you would get sine squared x plus 1 divided by 1 minus sine squared x equals 1. So let's see, maybe I'll start by multiplying the cosine to the other side and combining those two 1's into a 2. So I see 2 minus cosine squared of x is equal to cosine squared of x. Okay, cool. What would you want to do next? Get all the cosines on one side. So I guess that means I need to add cosine squared to both sides. So I'll get 2 equals 2 cosine squared of x. What next? Divide by 2. So I'll get 1 equal to cosine squared of x. And now I can Gesundheit undo the square by doing a square root. So I'm going to say something slightly wrong, and you'll tell me how to fix it. So I'll get cosine of x is equal to 1, because the square root of 1 is 1. But I'm missing something. A lot of people said something, and they said it like slightly off cadence from each other. So people said plus or minus, right?
Yeah.
Okay. So I get cosine of x is equal to plus or minus 1. So I now have two equations to solve. Cosine of x is equal to 1, and cosine of x is equal to negative 1. In looking at the unit circle, what angles on the unit circle do you see which have cosine equal to 1?
0, 2 pi.
0 and 2 pi. But in fact, really that should be like 0 and then 2 pi and 4 pi, 6 pi, 8 pi. So any multiple of 2 pi. So anything of the form 2 pi k. What angles on the unit circle do you see which have cosine equal to negative 1?
Pi.
Pi. And that's the only one in the unit circle that you see? So the other one is x equal to pi. But once you find the solutions that you see on the unit circle, you add 2 pi k's. Nice. So I get a solution consisting of pi plus 2 pi k and just 2 pi k. How did that compare with what you got by thinking about tangent? Same. But maybe the solution you got thinking about tangent was a simpler looking set of solutions? Maybe I'm putting words in your mouth, but did you wind up with just pi k doing it your way? So, it looks like we have maybe two competing solutions, though you told me they're the same. Is it clear that those two give you the same sets of solutions? Yeah. This is all multiples of pi. Here I see all even multiples of pi and all odd multiples of pi. So one thing we even see is a simplification. X equal to any multiple of pi. Cool. How do people feel? People feel pretty okay? Would people like to also now see me chase through the solution that's like started in blue? Yeah. Let's do that. So there is another equation that I would like to solve for x. And maybe I'll even let you tell me what to do. What's the first thing you did?
I substituted tangent squared x t.
Mm-hmm. Good.
And then I just added the t squared and then subtracted 1 to the other side. And then I got 2. And square root.
And this time you don't need a plus or minus because negative 0 is 0. So you just need to solve tangent of theta equal to 0. And, well, you can play the same game. What's the solution between, what is a point on the unit circle you see with tangent equal to 0? 0, I guess? And once you find one solution, you find all of them because it's tangent. Nice. People feel okay about solving trig equations? Yeah.
If it was tangent equals 0 at 0, would that be undefined?
Ah, so tangent is equal to 0 at some points. Right, tangent is the slope of a line. So that line has no slope. So tangent of that angle should be 0. Tangent is undefined at some point. Tangent of pi over 2 is undefined. So definitely pi over 2 can't possibly be an answer. Does that actually address your question?
I thought that tangent was sine over cosine, and cosine is 0 at.
Sine is 0 at 0.
Oh, yeah.
Cosine of 0 is 1. Yeah, so that's definitely something you should worry about. If you report a solution, it better actually be in the domain. But I think we're okay on this one. Any other questions? Cool. So I would like to Now, start up something new. I would like to start thinking about equations which you can't solve for x because they're equations which are always true. I probably should have started this out at the beginning of the day. That would have been the efficient answer. Let's think about trigonometric identities. Oh. Well, counting is difficult. Did I shot anyone else?
Actually, can I take one of the
Okay. So let's start with an example of an identity. So we talked a lot about solving trig equations. But what if I asked you to solve this trig equation? What if I asked you to solve that? So let's chase through and let's think about it for a second. What x values make that equation true?
It'll just be all real numbers.
All of them. Maybe I'll even say all numbers. There's a way of making sense of what trig functions at complex numbers mean. We won't do that in this class. And they continue to satisfy this equation. So the solution is just all real numbers. This equation is always true. And that's useful because if you have an equation that is always true, well, that means you can use it when you solve other equations. Right? Like we did that a lot with the Pythagorean identity. Since we know this is always true, we can use that fact. So the Pythagorean identity says sine squared of theta plus cosine squared of theta. X's are useful, so I'll use x's. That's equal to 1 no matter what x is. And that's what it means to be an identity. No matter what number you plug into sine and cosine, this equation is always true. An equation which is just always true is called an identity. And you know a bunch of identities already. You can express things in terms of sine and cosine. What is tangent of theta in terms of sine and cosine? Sine theta over cosine theta. As long as both sides actually make sense. There's an identity. That equation is always true no matter what theta is. Similarly, do cotangent secant and cosecant have similar equalities? Yeah. So you know a bunch of re-expressed in terms of sine and cosine identities. The even and odd identities. Is cosine even or is it odd? Is it even? Is it odd? Let's get your graph. Just draw them all. Is that a graph of sine or of cosine? Cosine. If I take that graph and I reflect it over the y-axis, do I get the same graph again?
Yeah.
So that means it's even. So cosine is even. What does that mean cosine of negative theta is? What can I do with that negative sign?
Take it out, or no?
I can just erase it. Cosine of negative is the same as the cosine of that thing. What about sine? Is sine even or odd? Odd. So what can I do with the negative sign inside of the parentheses of a sine? How about tangent? Is tangent even or is it odd? So there are some identities that you know. There's maybe one which is slightly more obscure, but it's still on that table of identities that we developed in the distant past. The adding pi over 2 identity. What's the cosine of theta plus pi over 2 the same as? Negative sine theta. What's the sine of theta plus pi over 2 always the same as? Positive the cosine of theta. Maybe I'll emphasize the plus sign. So, what's tangent of pi over 2 plus theta always the same as? So, enough people seem a little bit incredulous about this. You know what? Let's actually take advantage of this moment to prove a trig identity. So I claim that that equation is true no matter what theta is. But if that's the case, I better be able to convince you. So I think what I'm going to do is I'm going to go down here, rotate to the side, and let's do a slightly improvisational demonstration of a trig identity. Let's prove that tangent of theta plus pi over 2 is always the same as negative the cotangent of theta. And there's a general process that you want to follow a lot of times when you're proving a trig identity. And that is start with the side that looks more complicated and try to reduce it to the side that looks less complicated. Which of those two sides looks more complicated? The left-hand side. So let's take the left-hand side, use things that we know, and see if we can get it down to the right-hand side. So let's think about the tangent of theta plus pi over 2. Let's try to write down things that we know are true. And maybe I'll suggest this. What's tangent in terms of sine and cosine?
Sine over cosine.
Sine over cosine. So tangent of this angle will be the same thing as the sine of theta plus pi over 2 divided by the cosine of theta plus pi over 2. By expressing in terms of sine and cosine. So an important detail in the idea of proof is that every step you do needs an explanation. So what has happened in that step? I've just re-expressed things in terms of sines and cosines. All right, but tell me, what's the sine of theta plus pi over 2? Well, it's written down on your piece of paper above, right? What is that? The same as cosine of theta? So that means that the tangent of theta plus pi over 2 is equal to cosine of theta divided by, what's the cosine of theta plus pi over 2? Negative sine theta, by using the theta plus pi over 2 identity for sine and cosine. So the idea is once you have an identity which you believe, you can use it. All right, and what can I do with that negative sign in a denominator? Or maybe I should just ask instead, what is the thing that you see on the right-hand side the same as? Negative cotangent theta. So tangent of theta plus pi over 2 is equal to negative cotangent theta because cosine theta over sine theta is the same thing as cotangent theta. People feel pretty okay? And you'll notice that I wrote down lots and lots of words. Your homework assigned corresponding to this material should include lots and lots of words. Sentences and stuff.
already in proofs.
Yep. Yeah, you're proving trig identities. In fact, that's a proof of a trig identity, isn't it? If you want to establish something beyond a doubt, you should explain why everything that you use in your argument is true. And in general, this is a strategy you can use when you're proving an identity. You can look at the thing that you're trying to prove and say, well, there's one side that's obviously more complicated. Let's start by thinking about that. You can do some algebra to that side and use other identities that you know, and hopefully get down to the side that looks simpler. So my intent is to go through all of the examples in this note packet. I think I have enough time to go through one or two more. So let's try to verify a trig identity. Let's try to prove this trig identity. 1 plus tangent squared of x divided by sine of x minus sine of x times tangent x, I claim is exactly the same as tangent x plus 1 all over sine of x. Does one side of that equation look more complicated than the other? Yes. So that's not always true, right? Sometimes you wind up writing down an equation and both sides look equally complicated, and so maybe you just need to choose one of the sides, or maybe you can do something else first. Let's take the side that's more complicated and try to reduce it to the side that's less complicated. 1 minus tangent squared of x divided by sine of x minus sine of x times tangent of x. And you'll notice that I've even put like some guidance on the right-hand side in terms of what steps seem reasonable. This is also an explanation of what I'm going to do this next step. The thing which I guess I want to do is factor. Do you see any factoring you can do staring at that equation? Definitely everything in the denominator has a sign next to it, so I can factor out that sign. So the denominator is exactly the same as the sine of x times 1 minus the tangent of x. How about the numerator? Do you see any factoring in the numerator? Say that wrong.
1 plus 10, 1 minus 10.
So a fact that's being used here, and this is also subsumed in the word factoring. 1 minus tangent squared is, well, you could write it as 1 minus t squared. This is just going to be some scratch work to get motivation. That looks like something that you just know how to factor, right? 1 minus t squared is the same thing as 1 minus t times 1 plus t. And if you wanted to check that, you could just FOIL out the right-hand side and see that you actually get the left-hand side. So you can factor it to get 1 minus tangent squared of x times 1 plus tangent squared of x. Oh, yeah, yeah. Thank you. That's the trouble with standing for 2 hours straight. At this point, I'm sleepy. I make excuses. I would have made that mistake at any point. Do you see anything that cancels? So, by canceling, we see that this should be the same thing as 1 plus tangent of x divided by the sine of x. Did we arrive at the conclusion that we wanted to arrive at?
Yep.
Excellent. So here is a proof of an identity. This proves that 1 minus tangent squared divided by sine x minus sine x tangent x is always the same as tangent x plus 1 divided by the sine of x. I think we have time to do one more. So let's just move on to the next example in the list of canned examples. Let's establish this identity. Tangent times cosecant is identically equal to secant. And I think I have enough time that I'm going to do one thing before trying to go through and proving an identity. So if someone tells you an equation is true and then says, I want you to prove this identity, well, maybe you should convince yourself that the identity is true before you try to prove it. Especially if it's me who asked you to do it, because you know that I did things wrong. So let's do something to just convince ourselves that this is true before we prove it. Do you think I could like plot both sides of that equation? I could, right? Let's see if I actually get something that convinces me that it's true if I plot both sides. Let's plot them. So let's plot y equal to tangent of x times cosecant of x. And let's plot y equal to secant of x. So do those two graphs that it's generated look like they're exactly the same? And in fact, both Math will do some algebra for you. And it seems to say, yeah, they're actually the same. So let's try to confirm that identity now that we believe it. So in general, especially in the homework, if you go and try to prove a trig identity and it seems like really, really hard, maybe it's because you're trying to prove something that's not true. Sketch a graph, see if you believe it afterwards. Let's try so between tangent x times cosine, between the two sides of that equation, is one side obviously more complicated? The side that has two things instead of the side that has one thing? And there's no like factoring to do on the left-hand side. It's already a thing times a thing. So let's just try to rewrite everything in terms of sines and cosines and translate back. What's tangent in terms of sines and cosines? Sine x over cosine x. What's cosecant x in terms of sine and cosine? 1 over sine x. So I've done that by expressing everything in terms of sine and cosine. So there's even like some laws explaining exactly what happened. Do you see anything that cancels?
On our homework, if we like wrote like what you've been writing on the side here, would that be like enough of a description? Okay.
Sometimes, since you're not typesetting, you might wind up with space constraints. So maybe you should just go to the next line and explain what just happened. Like I wound up doing here.
Yeah.
So by canceling, maybe we'll even be more specific. By canceling the sine of x, we get just 1 over the cosine of x. Sometimes you'll be doing a step that seems more complicated and you'll want to write more ones. But if the step you're doing is simple enough to describe really quickly, that's fine. Okay, so I wind up with 1 over cosine of x. Is that what I wanted to wind up with?
Yeah, x is equal to.
Basically, because what is 1 over cosine? What is 1 over cosine of x? So what am I going to do? I will translate back to secant. 1 over cosine is the same thing as secant of x. Nice. So what will we do next time? We're going to continue in this same note packet. There's some homework posted for today. I think there's even an extra credit posted for today. Some of the problems in that homework will rely on some techniques that we haven't necessarily talked about yet. Nonetheless, take a swing at it. You can read more examples like this. You have the book. The book has exactly this.